$128,000 and some might argue a lapse.
$128,000.
Has created the jet-led flyer, this jetpack or personal propulsion device to reach top speeds of a little over.
You've seen these things before? I've used this video for a long time. It actually allows us to do some fun things in this class with Bernoulli.
And fly for about 186 miles. The reason is that this one leaves its fuel supply and power plants on the ground, or more appropriately on the water. That's it there, floating in a little pod on the right.
See the umbilical with a pump running behind it.
And rating from 130 to 300 horsepower is housed, along with the fuel to run it, in a floating mini boat.
Greetings.
The floating power pack is tethered to the jetpack by a long hose that delivers pressurized water to the control nozzles. The pilot has pitch control of the nozzles and a twist handle to control power. Unveiled at the Dusseldorf Boat Show and priced like a light sport aircraft, the company says it's already seeing interest, and that training to fly the maneuverable pack is included in the price.
There you go. Got to get one. I'm not sure what else. I don't know if there's a... Yeah, we'll use this today as well. And so I think there's a movie that goes with it, but not of him riding. Just kind of curious. And so this is the prone land speed record, face down, facing forwards. And this is the mechanism that he has on his bike to do it. And apparently 60 miles an hour by just pedal power. And so we'll play around with that to see if we can work out what his power input should be to be able to do what he does. So it's kind of interesting. So stop it. And yeah, this is a bit...
Nearly 2 years ago, Air France Flight 447 mysteriously crashed in the Atlantic, killing 228 people.
This
now,
is
the flight
2009.
recovered from the ocean floor, we know more about what happened in the final harrowing moments of that Rio to Paris flight. Here's Nancy Cordes.
The plane's black boxes revealed that the Air France pilots, faced with conflicting speed readings, didn't know whether to speed up or slow down. At 11:10 p.m., the Airbus A330 was heading into a powerful...
It's the flight that left from Rio to go to Paris, and unfortunately didn't make it.
And the plane began to roll to the right. Cockpit displays showed inconsistent speed readings, a sign that the external speed sensors, called
Pitot tubes.
were malfunctioning, or perhaps had iced over. "I have the controls," called one of the plane's two co-pilots. A stall warning went off, and he climbed briefly before pointing the nose down to pick up some speed. Then he leveled out and began to climb a bit, perhaps not realizing he was still going too slow. That triggered a second stall warning. But instead of pointing the nose back down, he continued to pull up.
The aircraft begins to roll. It begins to go from one side to the other side.
Mark Rosenker was chairman of the NTSB when the plane crashed in June 2009.
What we've seen in this cockpit voice recorder is two pilots extremely confused about what's happening on their flight deck, what's happening to their instrumentation.
It was now a minute and a half into the crisis, and the captain, who had been on a scheduled rest break, made it back into the cockpit. 20 seconds later, the co-pilot flying the plane said, "I don't have any more indications," most likely referring to speed readings. "We have no valid indications," confirmed the other co-pilot. As it pitched and rolled, the plane slowed even more and stalled, falling from 5 miles up.
Yeah, fine. We don't need to see anymore. Anyway, so yeah, unfortunate event, but you realize, of course, that all of that is predicated on this little tube that they have off the front of the cockpit, which if you get onto a plane in State College, as you walk up the outside gangway, you'll see it right underneath the pilot's window. And quite amazing, really, that in this day and age with GPS and satellite navigation, that we need those kind of indicators. Of course, satellite navigation will only tell you your ground speed if you have enough resolution on the plane. It won't tell you what the airspeed is, and of course it's the airspeed that controls the lift that you'd get from your airfoils. Belgian boy peeing, don't need to watch that anyway. So we're at 8:01. So, well, maybe we'll come back to those. I think they're all stalled out, so they shouldn't be overprinting what we'll talk about today. ScreenFlow's on. Presentation groups are live. And so I think in the middle of the week before last, I put you into groups. So there's a schedule. I think it was on the note that came out on Friday night at midnight to get in touch with your groups and initiate that. I don't think you need to do anything now, but you might make contact with them. Midterm grades should be done soon. Junpeng's working on them. The solutions are posted. I didn't mention that in the, people know that, do they? As you look on Canvas. So the solutions are posted, so you should be able to if you took a snapshot of your script, then that's pretty clinical. It's the number plus or minus 10%. So that's quite cut and dried. The classes last week, obviously, were online. And maybe it's worthwhile just giving a quick recap. Of the 3 classes, 4.1 was still in the statics category. Seems an oxymoron that you have accelerating fluids which are static, but static refers to the fact that the container is accelerating, and within the container, the fluid is static and not circulating much. And you'd have seen an example of a bus accelerating with water trapped between the dual pane glass. And there's certainly, I know that everyone's looked at that who wanted to, because that closed on last night at midnight. But the expressions after the manipulation of the static and accelerating equations are that if you accelerate a fluid horizontally, that's some acceleration. You define the positive accelerations in the positive directions of the axes, x or y and z in our particular case. And you can use that to get information on the slope of the curve just by simply manipulating the equations. There's a standard result that says that it's equal to the acceleration in the x direction divided by gravity plus az. Acceleration vertically is upwards, positive, but gravity, obviously, acceleration is downwards, and it's the negative of this line. So this refers to the slope. If you look at a quadrant of x and z, you know that this is positive, this is negative slope, just in terms of these being positive numbers. And so this negative sign matters because it defines the slope of the graph. So if you accelerate more, if you're not accelerating vertically, just running along on a straight path, then it's just ax over g. Ax is positive in the right direction. If it's accelerating to the left, then it's negative ax, obviously, because it's against this. And if you're not accelerating upwards, if you're not moving the container upwards, you're not having your coffee in an elevator, then the pressure distribution on this would just be the hydrostat, measured from the free surface here or measured from the free surface here. It would just be equal to dP dz equals minus rho g, unit weight. If it's accelerating, then you could imagine that if accelerating upwards, you think that you're pushing the water in your cup, mainly water, coffee, I guess, and so you think that it would be a higher pressure at the bottom because you're pushing against it, and indeed. So this would actually change so that if you're accelerating upwards, it would change its orientation to be adding the magnitude of this, right? So that defines that. Rotation accelerations, again, standard result from the equations, long derivations, but the bottom line is that the elevation of a free surface, if you take a container and you twist it around its axis, if you wanted to do that, I guess there are some industrial processes that try and centripetally separate minerals based on their density. Most dense elements will fly out further, centrifugal separation. Same as gold panning. The gold sits in the bottom, and you take out the other minerals off the top of it by shaking it around. It's basically the same principle. And the slope of this surface is given by this equation. This is the angular velocity, which is in radians per second. So 2 pi radians per second is a revolution per second, RPS. The angular velocity, the actual velocity that this point is traveling round, and I guess it would be, in a perspective, this would be v theta. So the coordinate systems are z and r and theta, an azimuth, as an angle between this. And so this actual velocity of this point skipping around at the outer edge of this container would just be the radius of what that point is multiplied by its angular velocity. But by definition, that's what the angular velocity is. And so to get the elevation of this surface, you can get it from the angular velocity, whatever the radius is where you are, gravity, and some constant. And so you have to define what that constant is. And we went through an example. If you know, for example, what the elevation z is at r equals 0, then you would know this. Why doesn't one work? It's got a memory. It's got a mind of its own, actually. I don't know what that's. So you'd know what this is. You'd know what r is. And you'd know what z is. You know what g is. So you could calculate what the constant is. And then if you apply it to some other location, then you'd be able to apply it. Yeah, okay. Now it's back with me. So you know all the terms in this if you know a particular location. It might be that you know this elevation here and this radius. Either way, you know all the constants here and you know this. So you can decide on the constant, comes in the integration, and then you can apply it to get the elevation at another point. If you want to get the pressure, you can also use the same thing. Again, it includes a constant that you need to determine. I guess if it's not accelerating upwards, then the gradient of this would just be dp dz, no, not x, dp dz equals gamma g, minus gamma g, minus gamma. So this would just be as if it was a static fluid. Right here, it would be just as if it was a static fluid. If it's accelerating upwards, then it would change just in the same way that this one has changed. It would be, if you're accelerating upwards, it would be flatter, higher pressure at the bottom. If you drop the elevator, or if you drop yourself down the elevator shaft, holding a cup of coffee, what would the pressure distribution be in that? You know that you're accelerating downwards at the acceleration due to gravity. So it's gravity minus gravity. And so the pressure distribution in your coffee would just be like floating in space for a while, right? Then all of a sudden, it wouldn't be so smart. And so that's why the so-called vomit comet is the parabolic flight of the NASA plane that goes up to a peak, and it comes over that peak and then falls down. At the top of that, at the apex of that peak, you're at 0g because you're falling down at gravity, and therefore you feel, the fluid feels exactly what you feel, the fluid in your body and your body feel exactly the weightlessness that you'd expect here. We talked about Bernoulli. I won't go through this. I noticed this morning that only 10 people had looked at 4.2. I don't think that's wise, I was going to tell you. I think it's, sure, it doesn't close until Wednesday, right? Tonight, yeah. It doesn't close tonight, but we're going to build on it. So I would advise getting preparation for this. And so we'll talk lots about Bernoulli along a streamline today, and we talked about that for 4.2 and 4.3, but 4.2 is specifically about behavior normal to a streamline. Actually, it's very similar to the idea of the centrifugal behavior. If you imagine spinning a weight around your head, then there's a force that you apply to that weight because it wants to go out. That's really what's controlling this behavior. And so something going over a bump is like doing something in this axis, so it's going around like this. And so you know that when you go over a bump in a car, you feel lighter in your seat than if you're going down into a dip when you get pressed into your seat. So it's exactly the same as kind of the idea of being pressed against the side of the wall of death, right, at the fun fair. And Bernoulli's expression is a little bit like the parallel to streamline one, which is P. I always write it as, if I do it in these terms, P over gamma plus V squared over 2G plus Z. I guess you could multiply them all by unit weight and unit weight and unit weight, and you'd end up with something like this. So this is parallel to along a streamline. So this is along a streamline, I guess. This is normal to a streamline. So we're going, these are the individual paths that a particle of fluid would take. This one starts here and goes through this locus here. So going normal to that, you get this expression. And so if you wanted to look at the pressure distribution as you went across this bump, it's a little bit similar to the case that we have for these other fluids. If the radius is infinite, right, then this term goes to 0. This whole term goes to 0. And if that term goes to 0, then you get P plus gamma Z equals constant. So this is just a manifestation of dP dZ equals minus gamma, right? You could, if you integrate this, you get this. So this means that the pressure distribution, if it's flowing horizontally, because this radius of curvature is infinite, you'd expect it just to be the pressure distribution you see in a static fluid. If you're going on the top of this, then this term is no longer 0, and you can't treat it that way. It'll be finite. And it turns out that if you're going over a hump, it's actually reducing gravity, just like dropping down through an elevator, and the pressure distribution would be reduced by some constant that you can calculate, again, by integrating this expression. I won't go through it today. It's in 4.2, kind of a lengthy process, but you need to play around with this. I guess the things you need to know are that the velocity will be defined at points, say, for 3 and 4. If you know the velocities at 3 and 4, you know the radii of those points as well. So you know this. Whoops. Thought it was going to revert. So you know the velocities at 2 points. You know the radii at 2 points. dN is equal to minus dz. So the coordinate system in this is z upwards. Positive z is upwards. And so n always points to the place where you're holding the cord and swinging it around. So these are the negative of each other. And so if you end up doing the integration, and there's a pretty simple example that we take from the textbook. This is from the textbook also. The punchline, I suppose, is that if you're going over a hump like this, it will reduce the pressure by some amount. It doesn't mean anything once you get into the solid, so that's why I drew the line here. And if you go on something that looks like this, then your pressure would look like this. It would be larger. So, and you'll be able to see that, just because of the sign of this term. So in other words, it gives you a pressure plus a depth, and this ends up not being a constant that you add to it, but it will be scaled with the value of its location along its length, and so it will be essentially a linear function. So that's that. So that's the kind of catch up on what was last week. So the fun that you still have to do if you're going to look at those videos. These are the expressions that we developed last week, if you looked at them. Along a streamline, we'll talk about today. I always write it like this in terms of a length. V squared over 2g is a length. Pressure over unit weight is a length. Adding apples to apples. The fact that it's constant means if you add it, you evaluate it at 2 points. And if you evaluate it at 2 points, We don't have to worry about these terms yet. We won't think about them, but these represent losses. But Bernoulli, without these terms, is for an inviscid, incompressible, weightless fluid. So the main thing is the requirements for Bernoulli are incompressible. Two is no vortices. Can't remember the other ones. Yeah, but we'll deal with them as we go through it. And so what we typically do is write it between a point upstream and a point downstream, as we'll do today, and solve for that. So we talked about that last week. This we won't talk about more, but you'll see it today if you look at your 4.2. And the things that we'll talk about, Air France flight XXX, whatever that was, Pitot tubes. We'll talk about free jets. We'll talk about continuity. And if we have a chance, we'll do two examples, one of the Jetlev and one of Graham, whatever his name was, doing his magic bike ride. So, Pitot tubes. The idea is, you saw it, it's a little hook tube on the side of a plane, always on the left-hand side, it seems. I don't know if there's one on the right, because you always board on the left-hand side of the plane and see it. Perhaps there's a complementary one on the other side as well, just for redundancy. Planes have two wings and two engines for a reason, I guess. Well, two engines anyway. So the idea of a Pitot tube is that you measure the pressure in the cockpit in a central annulus, which is this red, and also a annulus in the tube, which is this green. And those two annuluses pick up pressures, which are best thought about having a pressure. I'm going to write it out here. I'll call it A, and I'll call it B. And if we write Bernoulli, we get ZA plus PA over gamma plus VA squared over 2G is equal to ZB plus PB over gamma plus VB squared over 2G. And the easiest way to think of this is that obviously we're on a plane going forward at 600 miles an hour and the air is static, but it's easier to think of it as the Pitot tube being static and the air hitting us at 600 miles an hour, 500 miles an hour. So we'll do that. And so if that's the case, then we know that we don't know what this velocity is. We do know that the pressure out here is atmospheric. We could take it as 0, but that's not. And we know probably that the elevation of the tube relative to being 35,000 feet up, whoops, cancel out. Right? So these aren't 0, but they cancel out. We know we measure this, and we know that this is 0. Air is coming forward to us at 500 miles an hour. It hits the tube. It's a dead end. It stagnates, so the velocity here has to be 0. So VB equals 0. VB not equal 0. It's the flight velocity. PA essentially equals atmospheric, which will take as 0. And PB is not equal to 0. So if we solve for this, we would get VA squared over 2G is equal to PB minus PA over unit weight. Let's call it rho G. Boom, 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 boom. So this is equal to VA. So you can do all this stuff here, but you essentially have that expression here. PA, if it's atmospheric and we're using gauge pressures, which we probably would, equals 0 gauge. had a pressure transducer calibrated at sea level, it'd be that. Perhaps it's less than that. I guess actually you're 30,000 feet, same as Everest. Perhaps you're maybe 10% of that, as we saw in the calculations. But the bottom line is you can calculate that. And so what you want to get out of it is the velocity, very accurately what your velocity in terms of airspeed. Airspeed is the speed that the air is flashing over your airfoil, your wings, which is what's pulling you in the air and telling you when you're stalling or not stalling with your airspeed, and therefore you want to have control over that. So amazing still that you use those. And the problem, of course, with Air France was it was iced over. So if you ice over this entry, then it has no way of measuring a pressure from killing the velocity here, and therefore you get spurious indications of your velocity, and you have a problem as a result of that. You could imagine that if you measure, so certainly if you have air rushing past just an open hole here, or the backside of this Pitot tube, this is going still at VA. So this is VA, so the pressure here has to be the atmospheric pressure at A. So that's the idea here. If it's not, so this is the case for that, then the pressure here is equal to the pressure that you have out here, which is this. You can imagine that if you had a lip behind it where you're killing velocity, your velocity goes from V here to V equals 0, then this V equals 0 is going to be transferred into a pressure. You're killing the momentum of this. And so this would measure a pressure that's larger than the pressure at infinity. This one, because it's a ski jump going over, just like the system from this, a bit like this, you'd expect that it would measure a pressure that's less than at the far field pressure. And so you'd like it to be horizontal to be able to do this. And that's exactly how the tube works. You could imagine having a directional tube if you had an angle on this, so it hits the flow velocity at an angle. Obviously, the angle of impact of this is the component of this normal to this tube is a fraction of the magnitude of the real true velocity. It's going to be cosine or sine times that. And so you could imagine that if you had a Pitot tube that would look like this, if the flow velocity was coming in this direction, this would have the maximum pressure in it. This would have a lower pressure in it because it's skirting around it, because the angle of attack is, the real angle of attack is really only an apparent angle of attack that you're seeing. And so you could imagine by plotting the pressures of these three little ports, you'd measure the maximum pressure here, a lower pressure here, and a lower pressure here. And from that, you could triangulate on the velocity direction if you wanted to do that. Probably be easiest if you looked here, right? If it's coming in this direction, this would be max, this would be less, this would be equally less, and therefore you could say that this really is the direction in which it comes. Okay? First one, Pitot tubes. Second one is the so-called continuity principle. Principle, right? Yeah, not principal. And that is that mass flow rate in equals mass flow rate out. So the other thing I neglected to mention about Bernoulli is that it's also steady state. So in other words, if you look at this stream flowing down the river, oops, and you take a picture of it now, and you take a picture of it 10 minutes later, then the velocity at this point and will be the same 10 minutes later as it was 10 minutes previous. The velocity at this point will be the same throughout the time between that 10 minutes. So it's not changing. So as you go downstream, the velocities are certainly changing. It's going from a low velocity here to a high velocity here. You know that because the cross-sectional area that's flowing across, which is A, is shrinking. So if this is cross-sectional area A1 and this is cross-sectional area 2, A2, you know that the volumetric flow rate Q1 is equal to A1 V1. And if the flow rate across here is equal to Q1, that has to be the same flow rate across this boundary here, which is Q2. If you're not having the same volumetric flow rate, so meters cubed per second going out as you have going in, then it has to accumulate somewhere. Simple idea of a bucket, right? If you put 1 liter a second in and have it flowing out at 1 liter a second, good. It stays at the same level. If you have it going in at 2 liters a second and 1 liter a second out, it's going to overflow because it's going to change its volume. So if it's staying the same geometry, by definition, it has to be steady state and therefore flow rates in. So this means this is equal to Q2, which is also equal to area 2 times velocity 2. And so you can take from that the cross-sectional area times the velocity at upstream, and the cross-sectional area times the velocity downstream are the same. And the best way for us to do this is to pre-multiply it also by the density of the fluid. Because it's actually really not it's only a conservation of volume if the density of the fluid doesn't change. If it's a compressible fluid, and we said that for Bernoulli it only works well for compressible fluid, it's not true. It's really the mass flow rate that comes across this has to equal the mass. So 1 kilogram a second into the bucket, 1 kilogram a second out, perfect. 2 kilograms a second in, 2 kilograms a second out. It can't stay the same configuration in the bucket and it flows over. So all the conservation equations you'll deal with in your porous media flow for petroleum engineers and environmental systems engineers are mass conservation. Mass in equals mass out, typically of a differential volume. Scary differential volume, but not so scary once you understand this course. And so we use this because in some cases we can write Bernoulli's equation between upstream and downstream, but it may be that to solve this we need to know 5 of these variables to solve for one unknown. It may be that we have 2 unknowns that we don't know. And if that's the case, if we can link the magnitudes of the velocities in some way, by substituting, we can rearrange this to say that V1 is equal to V2 A2 over A1, rho over rho. This is equal to 1 if it's Bernoulli, or they could be changing. Then immediately we've taken 2 unknowns and made them into 1 because they're linked. They're linked by if we know the cross-sectional areas. And so we'll use that. So Pitot tubes, conservation, continuity principle, conservation of mass, we'll also talk about it, is really volume in, or it's, I guess you could say it's volume rate in and volume rate out. And if we multiplied by density on each side, it's mass rate in equals mass rate out. And it is easy to think of it as a bucket. This is into the bucket, out of the bucket. Don't care what's going on here, but if it always has the same configuration, in other words, this water level isn't rising and falling, it's always the same contour, then it's also steady state. Can't remember what the 4th requirement for Bernoulli is, but isothermal, that's it. Number 4 is isothermal. We don't care. Actually, it works quite well for compressible fluids, which would be air, and we'll use it for examples with compressible fluids. So Pitot tubes, continuity, free jets. So free jets is the simplest of our standard results, I guess, for applying Bernoulli. We can write Bernoulli, well, I told you that I like to write it in my own way. If I write it in my own way, take flow between 2 points, you need to be on a streamline. So a point here will flow through the tank and will come out of the tank here. So we can write pressure 1 over unit weight plus V squared over 2G at point 1 plus elevation Z1. P2 over gamma plus V2 squared over 2G plus Z2. So what do we know? We know this location here. We also know that A1 V1 is equal to A2 V2 from continuity. So we know from that that velocity 1 is equal to velocity 2 times A2, yeah, thank you, thinking ahead of me. Yeah, thank you. So, A2 is small, so this will be a small number. In the limit, it goes to 0 if this is tiny and this is huge. So a large tank is code in questions for the fact that this velocity is 0. Makes life easy if this velocity is 0 in some cases. And so we know that this is equal to 0. We know that P1, if it's atmospheric, is equal to 0. We know that where it squirts out of the tank at this bottom, then if the pressure acting horizontally is going to be atmospheric, which is 0. Acts horizontally, it acts in unidirect, in the same, in all direction. So this also has to be 0. And the only things that we're left with are the differences in elevation. And so we can rearrange this as, if I just do it here, it would be V2 is equal to Z1 minus Z2. This term here, multiplied by 2G squared, yes, thank you. So in other words, V2 is equal to Z1 minus Z2. Z1 minus Z2 is h, the height. I'll write it standard form 2GH square root. Standard result, which you see here, right? And so all we've done, well, we've used continuity to rationalize huge tank, big surface, then this has to be 0 velocity. This is not 0, and it's given by the height of this. We could also write it at 0.5. I won't do that. But if we did write it at 0.5, we'd find out that V5 is equal to 2GH plus H square root. It's just equal to the extra height that we've added to here onto Z. And so if you recognize this, this is exactly the same as the equation for a weight falling in space. No different. It's just that the weight has fallen by the time it gets to this point. It's fallen through some height h. So it starts off with a velocity which is given by the, if you like, the potential energy of the system. The height of water above it is driving it at a velocity which is equal to it having fallen from the top of the surface of the tank, 0.1, all the way through to 0.2. It clocks the velocity v2 at 0.2, which would be the same as this going through the gate, through the finish line, and it's at that velocity. So this velocity is identical to dropping a weight from this height here. And as it keeps on going, it has to be this. And I guess the other interesting thing to think about this is that you could also write continuity as V2A2 is equal to V5A5. And so if you rearrange that to write it as in terms of V5, V2 is equal to A2 over A5 equals V5. Then we've said that V5 is larger than, well, actually that's not the way we want to write it. We want to write it in terms of A. So we want to write it as A5 over A2 A5 over A2 is equal to V2 over V5. So this means that this is small, this is large, this is less than 1. This has to be less than 1. So it means that A5 is equal to, A2. The width of the jet below it has to be less than it is when it comes out of the tank. So it has to taper down as you do it. I've got a video that we'll look when we look at continuity that shows you water coming out of the faucet. It starts off ½ inch wide and it ends up ¼ inch wide, a foot below. And you'd expect that exactly from what we now understand about this system. And so, yeah, I'm pretty sure I've said everything I want to say about this. Yeah, that's it. So that's all we had to talk about today. What we might want to do is make the same, try and look at the other videos that we looked at before. One of which was this. And so, oops, I want to turn the volume off. So this is the so-called $128,000 jet lev. And so what would we want to know if we were designing one of these? I guess we'd want to know what kind of flow output we'd want to have coming out of the jets to be able to lift a human. And from that, we'd be able to size the size of the pump that we'd have to give the flow rate that would to give us that behavior. So the question is, can we do that calculation based on what we now know about Bernoulli? And the short answer is yes, we can. So I don't know, we can start there as easy as anywhere else. So this is the idea. So let's make it a simple geometry. That's not a simple geometry. And I'll go towards my plan, starting at points 1, 2, and 3. And we have Bernoulli. P v squared over 2g. Maybe just write in terms of velocity and elevation. So those are our three things. P is probably large. Right? Have a pressure inside the container. It's forcing it out of here. It's in a big tank. So from our big tank idea, it's coming out of here at a big velocity, but within the tank, because it's a big tank, why should it be moving at all? So let's make it 0. And the elevation would be z1. And this would be z in general. This point here, point 2, would be z2. Velocity is big, right? I suppose I could write it as v2. And the pressure, from what we said before, the pressure acting horizontally in this direction is atmospheric. So by definition, it has to be 0. And then point 3, what do we know? It's hitting the ground, hitting the water. Actually, essentially the water is hitting a flat surface of concrete. That's why people jump off bridges. It feels like a concrete when you hit the water. So this is, the pressure is not equal to 0. It's big pressure. And it would be P1. And its velocity would be equal to 0. And its elevation would be equal to C3. So we've got Billy Boy sitting on top of this, and Billy Boy, or Wilhelmina, to be fair. Well, it won't be fair for her if she weighs 100 kilos. 100 kilos is 220 pounds. So if we want to calculate this, then we could be able to write the behavior in terms of the pressure that is exerted in this. So what we'd like to know is pressure 1. What is this pressure? So let's write Bernoulli between points 1 and 2. Plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. Let's collapse these down onto each other because we don't really care that they're far apart. It could be a small jet coming out of it. So let's write Z1 equals Z2, in which case we get rid of these. They're not 0, but they're the same. What else did we say? V1 is equal to 0. P1 is not equal to 0. And P2 is equal to 0. So we've got a simple equation. We've got the fact that P1 over gamma equals V2 squared over 2G. And from that, we can take that to get P1 is equal to rho G V2 squared over 2G. Rho V squared 2 over 2. And we just have a simple force diagram to solve. Oh, that is the way I wanted it. This is P3. Oh, yeah, sorry. No one stopped me. Yeah. So this is equal, it has an area and it has P3. So the force acting upwards is P3 times area 3 equals W. Yeah. So this goes here. And so what do we want to solve for? We want to solve for rho V2 squared over 2 times A3 equals W. This is what we want to solve for. And so we want to have 2 times W over A3 divided by rho is equal to V2 square root. Hopefully that's right. Is that right? 2WP over, yeah, fine. So what are some numbers? On a good day, I'm 204. On a bad day, I'm 210. It's close enough to 220 pounds. $100 kilograms equals 1,000 newtons as a force. W is a force. W equals 2 times G, essentially, if it's 10 meters per second. Area, I took it as 4 inches. 4 inches is 10 centimeters. Area equals 4 inches by 4 inches equals 10 to the minus 1 meters squared, 10 centimeters. So V2 is equal to 2 times 1,000 newtons divided by 10 to the minus 0.1 of a meter squared area times 1,000 kilograms density of water, square root. And so if we put numbers into this, this is 10 to the minus 2 times 10 to the 3 divided by 2 times 10 to the 3. Am I missing something? Yeah, okay. So these cancel out. This becomes equals to 2 times 10 to the minus 2. This is all square rooted. And this will be in meters per second. And so velocity 2 is equal to 1.44, isn't it? Something like that. Times 10 to the minus 1. This isn't 10 to the minus 2, this is plus. Equals 14 meters a second, which is 1 meter a second is about equal to 2 miles an hour, which is about 30 mph. So you know that to be able to lift a person off the ground, you've got to be squirting water out at a certain velocity and a certain flow rate. So you could size your pump to be able to do that. If you wanted to calculate the work, this is W, which is work, equals velocity times distance, velocity times force, which is just equal to W times velocity. W was equal to 1,000 newtons times velocity was 14 meters a second, which is equal to 14 kilowatts. This is weight, this is work. So you need a 14 kilowatt motor to be able to at least do it, not accounting for any losses that you'd have. So immediately you've been able to dimension something. You know that for the characteristics of your system, you need to get water going out through a nozzle so it hits the bottom of the water, the surface of the water at 14 meters a second. And to do that, you're expending something like 14 kilowatts to be able to do that. So you need an engine that's capable of delivering that. And that engine has to, since energy is conserved, it has to at least have an output of that, not accounting for the losses in the system. So it would be using electricity at least that rate if it's run on batteries, and it would do that. Okay. That's it. So have a look at your 4.2s and 4.3s. 4.2 is just Bernoulli along a streamline, which we built on today. We'll do some more examples on Bernoulli, I guess, tomorrow. Okay. Thanks very much. Great. Thank you. Great, thank you.